Hi, this is Nalini Elkins with Industry Network Technology Council. Please let me know if you can hear me okay. This session is being recorded. Yes, great. I'm getting signs that the sound is good. If you have problems, just go ahead and send me a message, and I will see what I can do. So thanks so much for coming. Just a couple of words about me. I am president of Industry Network Technology Council, which is a nonprofit industry consortium. I encourage you to join. The membership is free so that you can vote on our board members and affect the agenda. I have been working with IPv6 for many years and am now in the field of cryptography. So what we have done in the last two sessions is gone over a lot of terminology. And in this session, what we're going to do is to put things together and set the stage for what we're going to be talking about in the next few security webinars, which is in-depth going into how TLS and MLS in particular work. We will also discuss the implications of a quantum computer on some of what we have been talking about. These days, whenever you're talking about security, you really need to be taking post-quantum into account. So let's go ahead and get started. If you have questions, go ahead and send me a question in the question window, and I will get to it at the end of the call. So let's talk about how all these concepts that we've been talking about are actually implemented. As I say, we've talked about hashing, signing, keys, all that kind of stuff. But it's all well and good to have these concepts and these mathematical algorithms. What is it that actually goes over the wire and how? So what has to happen is all those cryptographic functions and primitives and calculations have to actually be implemented in a protocol. And these protocols are TLS, transport layer security, message layer security, SSH, IPsec. For example, these are the kinds of protocols that are used. And we will go over TLS and MLS in great detail in the next few sessions. So what is the process is this, and this is who generally does it. So NIST, the National Institute of Standards and Technology in the United States, has a disproportionate influence on what happens in the world. There are other organizations, other forums which standardize ciphers as well, many in different parts of the world. But I will say, I will just use one for example, as I'm going to use NIST as a stand-in for these bodies, knowing that there are others. But as I say, the United States organization NIST has a disproportionate influence, and many organizations follow its lead. So let's take the case right now that we've been working on most recently, which is that of post-quantum algorithms. And so NIST would standardize the new ones, and also it has standardized the ones that we've talked about in some of the previous sessions, which is, of course, DES and AES, which are the symmetric algorithms. And as we saw, for very good reasons, DES was deprecated. They also standardize the asymmetric algorithms, RSA, Diffie-Hellman, elliptic curve, and so forth. And of course, the new quantum ciphers, which we will talk about a fair amount down the road here, because those are based on quite different mathematics. So once that has been done, or sometimes overlapping it slightly, the IETF standardizes the protocols. For example, if we take TLS, what are the packet exchanges? How does the handshake work? You have a client hello, server hello, what's in each packet? And within these packets, the symmetric and asymmetric ciphers are used. And what is the format of the data packet? In TLS, we'll see there's a record layer format. And then something called formal security analysis is quite often done. And I will say, one of the very good things about the IETF, in particular in the last few years, is that formal security analysis done by generally by academia who specialize in doing security analysis of protocol is done alongside of protocol development. And I will say that that is one of the strengths of the IETF. There are other bodies which standardize protocols for other layers. Of course, IEEE will standardize, the layer 2 and lower portions of the stack headers. And ETSI and some other organizations do try to standardize protocols for the transport and the IP layer. But just, I will say, as a de facto standards making body, I will say it's generally the IETF who is looked to for the de facto standard of what happens on the internet, and of course intranet. There has been some struggle about that, but this is the state of events today, and I would say not expected to change, in my opinion, for the next bit yet, although who knows. There is a new working group at the IETF. It's in the research area for formal security analysis. That's a very, very interesting group, and down the road we will have someone talking about what security analysis is, because I think it's a fascinating area. So once this packet format and so forth is defined, if you're going to use it, it has to be actually implemented in cryptographic libraries. And what are these libraries? For example, one of the most widely used is OpenSSL. And OpenSSL is an interesting cryptographic library. It is developed it's open source. It's open source, and it's developed not by any one country. There's an open source group that supports it, and last I looked, they were completely independent. That is, not under the Linux Foundation or the Apache Foundation or anything like that. They are a standalone organization. And it's again, I will say OpenSSL has a disproportionate impact on the security of the internet. It's an open source library that many implementations use. It is in some ways one of the de facto standards of the internet. And of course, supported by a small group of open source developers. You can fork it, which means create a new version with different code, and many people have done that. There's also embed TLS, and that is supported by ARM, and it is mostly for low power devices. Again, that's a very interesting cryptographic library used in particular for IoT. Bouncy Castle is for Java. It's the Java crypto library. Again, quite widely used. Open source, I believe that one is too. There are others, of course, Wolf SSL, a number of others, but these are some of the basic ones. So the point being is that if you develop a new cipher suite or a new packet exchange, somehow it's got to get into these libraries to have wide implementation, generally. So once it's in the library, then it has to be actually called by a program. A program has to be coded in a programming language. Generally, you have languages such as C, C++, C#, etc. And of course, there's whether Java is necessarily compiled. Yeah, I mean, it is compiled. It's an interesting discussion of that, which we will not get into. But in any case, the compiler for these languages has to also be modified to support these cipher suites. And of course, protocols can be embedded in other protocols. For example, TLS is in many other protocols. And once you get to an actual C++ compiler which supports these new cipher suites, say for example your new post-quantum cipher suite, then is when you can actually create a program. And some of these could be your homegrown applications or vendor provided applications and so forth, many of which will do a TLS exchange. Or you can have something like Apache, Tomcat, your database server, DB2, MySQL, whatever, proxies. All of these then will embed this new code. You can see there's quite a bit of lead time involved, and when we're talking about making changes, there's a number of years which could be involved in doing all of this. And of course, it's one thing to change it if it's in software, but if some of these protocol exchanges or ciphers are in hardware, that's even a much more tricky area. And many of the cipher suites and the encryption and decryption functions are indeed offloaded to hardware, because rightfully so in some ways, because they're computationally intensive, and it's probably faster, sometimes much faster, to do it in the hardware. So that is what is done quite often. And so you can see too that there are many platforms involved. Some of these are proprietary, some are open source, and Linux, for example, has, as you are well aware, many variants, some of which are compatible and some not so compatible. For example, you'll have one stream, which is, for example, I would say the Ubuntu and such like Linux stream, and then another stream with FreeBSD, which is a different kernel. So, and then of course the multiple mobile platforms, Android, iOS, Apple iOS, and so forth. But then moving on to the IoT and mainframe. So it's quite a long process to get things implemented. What what we have been talking about, and which we will talk about at fairly great length when we get into it, is what is going on at the IETF in terms of these protocols. So when you're talking about IETF, quite often you're talking about you're living in the world as it will be 4 or 5 years from now. And when you're talking about quantum and post-quantum, that's likely to be 10 to 15 years from now. But given how many things need to be changed and how complex this area is, better to start learning now so you can catch up on it, sneak up on it, as we say. So you have a chance of really understanding what's going on before it really hits you in implementation. And so that's where we are at most enterprises, which is it hits you in implementation. And so a lot of times enterprises only get involved at that level, which is they put up some new application or make a change for some reason, and there's a problem in the application, and there's a mismatch possibly in Cipher Suites or TLS versions, and things don't work. And as I say, that is the tail end of what happens. Or, of course, there's a vulnerability that is found. And so when the vulnerability is found by some academics or white hat hackers or so forth, that leads to a Cipher Suite or TLS version being deprecated. So then you have to migrate, which leads then possibly to the problem above, which is a mismatch. Or timing problems. I've heard of timing problems where things fail also. The other thing is TLS is embedded in many middle boxes, IDS, IPS, firewalls, etc. And if there's a version change or so on, then all the middle boxes need to know about that as well. And it can sometimes cause problems with network management, as we see with the TLS 1.3 issues. So who is involved in the ongoing operation of TLS, for example, or other protocols? So there's a bit of a war going on. There are people who wish to hack into these protocols or to steal data, to actually steal financial transactions or whatever, And so they try to find vulnerabilities within the protocol so they can do their evil misdeeds. Academia and other researchers try to find vulnerabilities before they do. So this is an interesting discussion, and which you will hear a lot of at the IETF. It's kind of interesting. We were just looking actually a couple of days ago because we believe we found a potential way to do malware. And we were looking for a bug bounty for that. Why not get a little credit? So there are quite a few organizations which are involved in this arena, some for-profit, some non-profit. Non-profit are organizations such as Certs and of course, NIST, who tracks vulnerabilities. There are, of course, I'm sure you know those better than I. And then, of course, the for-profit organizations. And one of the interesting things that I hear, in fact, somebody said that when I was talking to them about post-quantum stuff, and they said, well, the vendors will take care of it. And of course, vendors will take care of things. You need to understand, of course, that if it's a for-profit company, their motivation is to make the most money for their company. So let me leave it at that. So for enterprises, I encourage you to come to the IETF and come consistently, because you will hear what is going on all over the world and absorb it in a way that it's almost hard to even quantify, because it's in the, there's hallway conversations, things are in the ether about things that have happened, things that are that people have found. It's a strategic advantage to you and your organization to have a fairly good idea of what is going on all over the world and what is likely to happen in the next 5 to 10. I enjoy this quote by Eleanor Roosevelt. I don't need to read it to you. Is do not be those people who just wonder what has happened. So TLS versions, if we just look at TLS in a deep dive kind of way, you'll see that TLS 1.0 lasted for quite a few years before it was deprecated. We now have TLS 1.3, which was released in 2018. There is talk about freezing TLS 1.2 and deprecating some of the key exchanges. That is quite an interesting development. We'll talk some about that today. So there are many cipher suites that are used in TLS, and a number of them are deprecated. That is, not recommended to be used as vulnerabilities have been found. And you can see down here, it's like a lot of the ones that have DES in them have been moved to historic status. TLS 1.3 cleans up the set of cipher suites a great deal, and we'll talk about that in the webinar on TLS. There are only 5 cipher suites supported for TLS 1.3, except, of course, as we get into the post-quantum world. It's an interesting thing. It's like you start out trying to clean up things, but then life intervenes. So let's talk about the security area at the IETF. And the reason we're talking about this is that in this arena, the IETF has a disproportionate impact on what happens in the world. For example, the TLS, Transport Layer Security, is standardized at the IETF, and it is the most widely used security protocol in the world. So I will say there's a great deal of responsibility involved in maintaining this protocol. So the security area, and you can go see the About screen for this. Here's a link for it. It has all the working groups that are focused on security within there. That is how the IETF is organized, and it looks at these various components of security, and they don't necessarily all have to be used in any one protocol. So, for example, integrity is done in a number of different ways. It can be a hash, it can be a checksum, some other way of assuring that the message has not been tampered with, a MAC, something like that. Authentication then really is the packet from who I think it's from, and it doesn't necessarily need to be encrypted or even authentic or even have integrity. It just says I am assuring you that whoever you think sent that packet is that person. or of course, if you may want to validate the client as well. So there can be client authentication. And non-repudiation is an interesting area, and in some amount of discussion, it's like being able to say that you did not. Some people want an assurance that whoever sent this can't say, no, I did not send it. So that's a very strict control. There's also, you also hear deniability brought up on this in this area. That non-repudiation and deniability are probably worth an entire webinar in and of themselves. But so we will move along. Confidentiality, of course, that's much more easy to understand, which is encryption. That's keeping things secret is how to do that. Of course, easy to say, easier said than done, because that's what we've been talking about for quite a few hours already. And then access control is how do you get to do these things. It's some of these areas have changed. It used to be we had just the big three: integrity, authentication, and confidentiality. But now non-repudiation and access control have been added. And within these, since these areas often use key management, that's very important too. And one of the interesting and complicated things about these protocols is that there are many different kinds of keys. You can have signing keys, you can have symmetric keys, asymmetric, public and private keys. So you have to be sure about which exact key is it that we're talking about, because the key and how it's managed, the keys are used for different functions. So these are the groups at the IETF, which are there. We will not cover all of these in any level of detail. What we will do is today we'll talk of some, as much as we can in the rest of this time, about some of the drafts and the focus of what's going on in TLS, and we'll touch on MLS. We'll do a number of webinars on MLS itself coming up, and PQIP. We'll touch on what's going on there. As I say, each of the drafts will take a webinar of themselves. So we'll do the best we can. What you'll notice is what is not there. You notice that OpenSSH and PuTTY, which is used quite often for SSH, is not standardized by the IETF. So who cares, right? Well, it matters because SSH is used by many, many organizations. And in fact, it's used for administrative functions, which can be critical. And there has been quite a great deal of talk lately about what cipher suites are used within SSH, and in particular when it comes to post-quantum. I encourage you to look at that discussion. It's an interesting area, and what we might do down the road maybe is to have a panel, maybe getting some of the OpenSSH folks as well as some of the folks in PQIP involved, because there is some of the cipher suites are not the ones that NIST has approved. Of course, they may decide to change, and there is still some. It's not we need a way to more formally test these cipher suites, the ones even that are standardized by NIST. And so as I say, I have my own issues with the IETF, but having said that, some of the smartest people in the world are at the IETF, and if it's not standardized by the IETF, it's a caution to you. Yeah, that's all I'll say. So this is the TLS working group, and it's an open group. You can go look at the list archives. All discussions are public and open intentionally because people should know what is being talked about as it affects all of us. And you'll see the active drafts, and these are the ones you'll have drafts which have been adopted by the working group, which means that they will become a product of the IETF. The process is that an individual submits a draft and proposes it to the working group for adoption. And if the working group approves it, then the entire working group will contribute to that draft, and it becomes then a work of the IETF. There are independent submissions which are not a consensus document of the IETF. And then of course there are RFCs which have gone through the entire process. So what I'm going to talk about today is some of the ones that have been adopted, and one which is an individual draft. And it is these. There's one for encrypted client hello, deprecating key messages, and so on. So let's talk about this. So the first one, and this is I've just copied the abstract. So this is their wording exactly, and you can go up to the draft and see exactly what it says. So the idea behind encrypted client hello is that even though TLS 1.3 has encrypted most of the handshake, that is, in fact, the handshake, the client hello and server hello are sent in the clear. Everything else, server certificate and etc., is encrypted. So, but some people feel that even the client hello, which is sent clear text, can divulge private information. And in particular, there's something called the server name indication, which is the target domain. So let's look at a client hello. I just did this a few days ago on my system, and you can see that it is going over port 443. You can see the client hello. And we will this is what we will spend a good deal of talking about in the next session, is how does TLS work? What is the protocol exchange? So this is getting you ready for that. So you'll see the handshake protocol, which is the client hello, the cipher suites that are acceptable, and then you'll see lots and lots of extensions to the client hello. And it is in here that people feel is the problem, because one such extension is the server name indicator extension. And you can see this one says very clearly that I'm going to Google. So what people feel is that someone else would be able to look at your traffic and say you're in a coffee shop or whatever, and you're on a network with everyone else, then someone could put a packet trace up, capture all your packets, and see what websites you are going to. So they feel that this is, it divulges a good deal of information. Also, too, you can have a server which has multiple domains, so the IP address doesn't necessarily tell you where it's going. Or you can, of course, do a reverse proxy and so on. The other side of this problem, of course, is that this is used by things, middle boxes, such as firewalls and smart intelligent firewalls and IDS, IPS, other middle boxes, proxies for functionality. So the question is, will this functionality break if this is done? So there's always two sides of the issue, and often the sides are privacy versus network management. Not always. Again, it's everybody has to do the best they can. Another very important draft is deprecating RSA and static Diffie-Hellman in TLS 1.2. TLS 1.0, 1.0, and 1.1 are already deprecated, and 1.3 does not support RSA and static Diffie-Hellman. So it is only TLS 1.2 which needs this. So this is, we've talked about this at great length on what the implications are. And do send me a note. I'm happy to repeat that webinar on the issue of key exchange and visibility. We've talked about it briefly in the past few sessions, but as I say, I'm happy to repeat that. I've done that session quite a few times over the years, so I will not belabor that issue. Another thing which is quite interesting is hybrid key exchange. So the motivation is to start implementing post-quantum key exchange in TLS 1.3. As we saw, NIST has standardized a number of cipher suites, but how do we actually get to use them? You have to have a key exchange methodology and protocol exchange, and it is being done in TLS 1.3. In fact, just this morning, I saw some messages going back and forth where there is a draft to freeze TLS 1.2 and add nothing more to it. And so the implication, one of the implications, of course, is that post-quantum key exchange would not be available in TLS 1.2. So again, some impetus to move to TLS 1.3. There's another one. This is an individual draft. It's by David Benjamin. David Benjamin is one of the Chrome developers, works for Google. And it's a very interesting individual draft. I expect that it is very likely to be adopted by the working group. But it brings up a few concepts which are quite necessary for us to learn. And that's why I will spend some time on this. And one of the things is that each paragraph of a draft or an RFC is quite dense and relies on quite a bit of knowledge that you need to have before you can put it in context and even understand what you're talking about. For example, the document describes Merkle tree certificates for use within TLS. So of course you have to understand what is a certificate, which we talked about last time, what is a Merkle tree, and which we will talk about momentarily. And so even that sentence requires a bit of knowledge. And then, of course, what is a transparency service and key transparency? And this is actually talking about certificate transparency. We won't talk about that. We can talk about it. Send me a note if you want to talk about key transparency or certificate transparency. Those are areas which are being worked on. I'll dwell on some interesting points here. So we need to understand Merkle trees, because that is something that is being used more and more in cryptography. It is becoming a very important, well, it's not necessarily a primitive, it's a very important concept. And so we will dwell on that because we need to understand it. And it's non-obvious. And we will dwell on post-quantum signatures because that is the whole idea of what happens when you move to post-quantum. It is of interest. And because it is such an important thing, it's good to start thinking about it now, because it will have quite a bit of impact on us. What's interesting is that even if a cryptographically relevant quantum computer is not developed, what is happening now is the protections for the quantum computer are being built into the protocols. And so it forces us to have to understand this. Even if such a quantum computer is never built. What I will say, though, is that experts in the field believe that such a computer will be developed. 70% feel in the next 10 years, and I believe some 90%, some in the next 15. And given what all has to be changed, that feels like hardly any time. But of course, people are saving your packet traces today. And even 10 to 15 years later, some of the packet traces they have will contain very interesting data indeed. So again, this is exactly from that draft. I haven't changed anything. I've just highlighted something. So this is their wording. And again, this is an individual draft. It's the first version of this, as far as I know, and it will likely change. But this is at least the idea. So what we need to think about is that within the handshake there are quite a few signatures. So let's say we have a certificate chain. We've got the end user certificate, the intermediate certificate, the trust anchor, the CA, the root cert. You can have two signatures, and the signatures validate that these signatures validate that the certificate is indeed from who you think it came from. So in an intermediate cert, you may actually have another extra public key. If you're using certificate transparency, you may have a signed certificate timestamp, and that can have another signature. If you're doing OCSP, Online Certificate Status Protocol, you may have yet another signature. And interestingly, if you just do a packet trace on some of your TLS sessions, and I do see OCSP being used a great deal these days. So it's more and more becoming quite important. Certificate transparency and key transparency, as I say, need a session to themselves. So I won't go into it a great deal because we need to focus on this. So today we may have relatively small signatures, say maybe 32 bytes or 64 bytes, but the post-quantum replacements are quite a bit larger. Again, this is right out of their draft. For example, some of the new ones. You'll have these are some of the new post-quantum cipher suites: dilithium, Falcon, and so on. And they are much larger. 1952 for the public key, 3293 for the signature, and then you may or you may have multiple signatures there. So then you're talking about, 15K sum of authentication, and with Falcon, they may be 4,000 or 7,000. So you can see there's quite a bit of change in terms of how much these are. It's a very interesting question as to whether for some algorithms, in particular symmetric algorithms, whether that is even an adequate key size. That, again, that's an interesting discussion that we have been having and that I am having with some others. But suffice it to say, changes will be made and the size of the signatures will become greater. And so you might think, well, how does this impact me? Well, just the other day, I was talking to somebody and they had a timing issue, mostly because they changed the size of the certificates. And so you can see if certificates, signature keys, and all these things grow, there is quite a bit of response time change to this, and potentially traffic over your network. In any case, it's something to be thought of. Is if you're going to do this per handshake and the size grows that tremendously, possibly we need to do something about it. And so what Benjamin proposes is Merkle tree certificates. It's an optimization, and so that keeps the subscriber key under 1,000 bytes. So let's talk about what that is. So essentially, we need to back up a bit and think about what the fundamentals of a Merkle tree are. Merkle tree is essentially a binary. It's a hash tree, which is based on a binary tree. So let's talk about what a binary search is. A binary search finds a specific value in a sorted list of elements. Keep in mind, sorted. So let's say, for example, we have the following numbers: 1, 2, 3, 4, 5, 6, and the 7 under the arrow, 8, 9, 10. So let's just say we've got this sorted set of numbers. So to do a binary search, we start taking it in half. We divide the list in half. We say there's the first half and then there's a second half. And we say, okay, the middle of the second half, the second half starts at 6. Is our number greater than 6? It is. So we know we need to look in the second half. Then we divide it again and we say, is it bigger than 8? No, it's less than 8. So we're looking in the first part. And then finally, we find the number 7. The reason this is important is that if you always did a sequential sort, if you went 2, 3, 4, 5, 6, 7, etc., then it would take you a great deal of time to find the number in a large list. If it's a very small list, obviously it doesn't matter. But if it's a long list, clearly it matters a great deal. And of course, remember, you have to sort the list first, otherwise this doesn't work. So now let's discuss binary and Merkle or ratchet trees. So what's a binary tree? So keeping the idea of breaking things in half and how that can work, you can do a tree structure. So A would be the root node, and it has 2 children. A has 2 children, B and C. B has 2 children, D and E. C has 2 children, F and G. And if you give them numbers, then you can create mathematical relationships within the binary tree, which make it very efficient to sort. And I will be going over this in fairly deep detail in MLS, because the ratchet trees or hash trees, which are used in message layer security, are based on this concept. And as I say, once you understand the structure, you can see how it's quite efficient to search a large tree. and that's what these are called. You have they're labeled the root, you have the left child and the right child, and then this is the parent. And again, as I said, there are mathematical relationships between these. So a Merkle tree, invented by Ralph Merkle, is a hash tree. So essentially what you do is you have data within this and you hash up the tree. So the parent has the hash of these, and then there's a root hash, which is the hash of all of these. These are, again, it's all based on binary trees and binary certs. So you can see that makes it a very efficient algorithm. And more these kinds of concepts are being involved in within. You can see the Merkle tree for certificates, and MLS, which is using a ratchet tree, which is a variant of a Merkle tree. Yeah. So here's MLS, which I have alluded to. So MLS is very, very important, and I think it will be one of the most important protocols coming forth. People at the enterprises have paid very little attention to this, as I say, but it will be very critical. MLS will essentially change the entire way that messaging or texting is done. One of the folks and main people developing this is from the Cisco WebEx team. I believe WebEx is using this internally. This is the idea behind these is that the current applications such as WhatsApp and Signal and so forth, they cannot support a group of more than 200 without trouble. Then the cryptographic, they fall under the weight of the cryptography required to maintain such a group. And with MLS, you can maintain many groups. The size of the group can be quite large, millions, I believe. And it is based on this Merkle tree or ratchet tree that I talked about. And we will talk about this in fair detail coming up. So let's end with PQIP. This is a group I would suggest that you follow. It will outline how post-quantum integrate how post-quantum is used in various protocols, because it has to be in quite a few places. And you'll see, it will not develop the cipher suites themselves, but it will ensure consistency and clarity across the various protocols. And so let's look at some of the terminology, and we can go over this in detail in an upcoming session. But you'll see already some of the things that we have talked about is some of the things such as what is a post-quantum algorithm, what is a traditional algorithm, and when you have a multi-algorithm scheme, which is the TLS calls it a hybrid scheme. I suspect they will change to using multi-algorithm as this becomes the more standard way of defining it. So, post-quantum, we're going to need many of these changes that we have spent a good deal of time talking about. That is being done today. You can see the NIST has definitely defined the cipher suites. The key exchanges are in the process of being implemented. Certificates and signing changes are being implemented. There's an open SSL library in experimental stage, which has the crypto libraries, and some of the rest of this is starting. So it will be a brave new world out there. So that's it for this session. Please let me know if there are questions. I have one, or if you want to raise your hand and talk, I'm happy to unmute you as well. But please be aware this webinar is being recorded. So there's a question about accessing previous webinar materials. All our materials are up on the Industry Network Technology and IIESOC, our Indian partners' websites. You can, they're freely available, and all webinars are recorded, and so there's a YouTube link available for these as well as the slides. Any questions from anyone? Otherwise, I hope this was useful information for you. And the very next webinar will be on IPv6, and then after that, we will do a webinar on how TLS works. If you think of questions afterwards, do please feel free to send me an email. Otherwise, thank you all so much, and hope to see you next time.